All right. Well, guys, I think it's about that time to get started here. We've got a few people with us. Hopefully, the rest of the class roster will make their way into Zoom soon. But thank you again for your flexibility this week. And you found your way over to Zoom and following instructions on that. I really appreciate it. As a quick reminder, I will be back next week. So in fact, I'm coming back this weekend. And so we'll be back in the classroom in person again this coming Tuesday. But at least for today, we're going to do another Zoom session. Also, I have office hours tonight. Don't forget about that after 8 o'clock if you want to stop by. And I am going to have office hours in Zoom tomorrow night as well. So today and tomorrow, Zoom only at this point. And then over the weekend, I'll be coming back into town and I'll send you an email with a preview of the week ahead and what kind of office hours I will have as we get back into person again. There is a homework assignment due next Tuesday, and it's got a few problems about uniform continuity in it, as well as some practice with the stuff that's on the board right here involving derivatives. So you should try to get started on that whenever you have some free time, and then you can certainly ask me some questions. You can shoot me emails if you'd rather not figure out how to get into Zoom with me, but I'm pretty sure you can handle that if you need to. But send me emails and or stop by my Zoom hours if you got questions on the homework. I will be around. It's not that I'm disappearing into the wilderness, but I'm transitioning back to California this coming weekend. I did grade the homeworks already that you turned in this past Tuesday. For the most part, they looked all right. I did put solutions into Canvas, so I didn't have a chance to grade every single problem on that assignment that you did on Tuesday. I gave you quite a few points just for that video assignment. So there may be some things you want to follow up about, or at least check the answers that I've put into Canvas, and then you can ask me, of course, if anything wasn't clear. But it's a pretty good set of homework problems that you did for the previous assignment, and definitely worth trying to make sure you understand everything from that assignment. Anyway, so it looks like we've got most folks are here. I'm going to go ahead and get started. And does anybody have any questions about any of that before I jump into the math today? Oh, let me get my chat box open here just in case. If you want to use the chat box to ask me something or to make a comment, feel free to do that. Or if you're also more than welcome to just unmute yourself and we can use the microphone. You can use your microphone if you'd like to get my attention. And let me know if there's any problems with either the audio or the video. If you're having any trouble seeing anything today, I'll do my best to help you out. Anyway, so on Tuesday, this entire week, we're basically talking about derivatives, yeah? And on Tuesday, we sort of did the basic background, the fundamental definition of the derivative, as well as some very, very fundamental theorems about derivatives. And I've put a lot of that content on this board here. In the box at the top, you see the definition of the derivative again, right? F prime of c. C is just some point in the interval I. I is the domain of the function. And f prime of c can be calculated two different ways as a limit. Yeah, so it's the limit as as x approaches c of the quotient f of x minus f of c divided by x minus c. That's your classic difference quotient that you would have talked about in your earlier calculus courses. But we can reframe it in terms of the second expression on the board there in the box, limit as h approaches 0 of the quotient of f of c plus h minus f of c all over h. They are both equally valid, and which one you use, if you're using the definition, you can use either one of them. And which one you use is mostly just a function of the algebra involved. Sometimes one of them might work out a little easier with the algebra than the other one. But mathematically, they are completely equivalent definitions. So you can use either one. If I ask you to give me the definition of f prime of c, You can give me either one of those limit versions and I will take it. They're absolutely equivalent to each other. And there's no big hardship in going between them, that's for sure. So anyway, we talked on Tuesday about that definition, and then we proved a few results. First of all, if that limit is a real number, that's going to mean that f is differentiable at c. Okay, so if it's actually in the real numbers, it exists and it's a real number, then f is differentiable at c. And I squeezed in a few of the big theorems from Tuesday on this board here. First of all, if a function is differentiable at c, it must be continuous at c. So keep that in mind. And the contrapositive of that would be that if f fails to be continuous, then it will fail to be differentiable as well. So you can use the contrapositive version of theorem 5.1 just as easily. Let's see, what else? Proposition 5.1, this is a whole bunch of the derivative rules, right? Derivatives respect addition and subtraction, no problem with that. And then we have the product rule and quotient rule. We proved the product rule in class on Tuesday, and I mentioned that we will do a group work next week to prove the quotient rule. I think I referred to it as group work number 11. I don't know why I said that. I think I was mixing it up with my other class. It'll be group work number 6 that we'll do that on. That was just a misspeak on my part. Anyway, the quotient rule, we'll talk about that next week when we have a whiteboard and we can get you guys up practicing it. And then we did the chain rule. I didn't write the whole thing out here because there's a lot of assumptions. You know, f has to be differentiable at c, g has to be differentiable at f of c, and you've got this interval I and this interval j and so on. But the main equation, I put that here on the bottom, that should look familiar, right? This is our good old chain rule that we learn in our basic calculus course. So these are a bunch of derivative rules that I just feel obligated to prove them in a class like this because you might not have seen them proven ever before. But we're certainly not going to dwell too much on this. Maybe I'll just do a quick warm-up problem or two with these rules just to make sure everybody feels solid on them, and also just to kind of get us warmed up. So I'll do maybe a warm-up problem or two, and then we're going to move on. We're not going to spend too long rehashing all of these rules. But let's just do number 1 here. So I'm going to make a function, I'll call it h of x. And let's not make it too complicated. I'll just make it equal to the sine of 3x, right? And then what I want to do here, guys, is try to find the derivative of h. So h prime of x. So this would be, a standard exercise that we could do. But now we're not going to do this using the original definition anymore. The idea here is to take advantage of the derivative rules, the theorems that we did on Tuesday. So to solve this one, the main thing here is to recognize that h is really a composition of 2 functions. There's the function that takes x and multiplies it by 3. And then there's the function that takes the sine of whatever angle you put into it. So that's 2 functions. And we do want to get the chain rule involved because it's a composition of functions, right? We're composing these 2 things together. And in using this chain rule, we just need to identify what is f and what is g. In the notation of this theorem 5.2, notice that the f is kind of the inside function. So when you look at your input x into this function h, the first thing that happens to x is it gets multiplied by 3, right? And the outside function, which is the second thing that happens, is that we take the sine of that, right? So I'm going to, just to make it very precise, I'm going to create those functions here. F of x is 3x, and g of x is sine of x. And in so doing, then we can notice that h is just g composed with f. So it really is in this order, because you'll remember when you compose functions, you do it kind of from the inside out. So you'll have the f on the inside, that's on the right, and then you'll compose with g, which is on the left, which is the outside function. So this is the way this would work. And so if I want to take the derivative of h, I'm really taking the derivative of g composed with f, right? So let's write it down. H prime of x. I'm not even going to identify a point C here. The C is just a fixed value, but it'll apply to any value of C. So we have to take the derivative of g, and then of f of x, and then times f prime of x. So this is just theorem 5.2. That's the chain rule. So by theorem 5.2, and what are the derivatives of these things? Let me just see if I can squeeze them in up here, guys. I hope this will work. I'm still dealing with a pretty small space to write. What is the derivative of 3x going to be? 3, right? So you can take that as a given. All right. The derivative of 3x is 3. You can obviously prove that. And then the derivative of the sine of x, we actually did that one on Tuesday as an example. So the derivative of sine of x was cosine of x. So I'm squeezing that in really small right there. Cosine of x is the derivative of g of x. So if I come down to my calculation here, the derivative of g is cosine of whatever we plugged into it. Now, in this notation, we're plugging in f of x. Well, f of x is 3x, so we would just put that right there. And then the derivative of f of x gets tacked on to the end of it, which is the 3. And that would be the answer. So just that simple, right? So you have the derivative. You could have handed that to a Math 150A student. They probably could get that right. Hopefully they could. If not, you need to tutor them on the chain rule a little bit. But yeah, that's just making it very formal with the notations of f and g that we have here on the board. Let's see. Maybe I'll do one more. Is that okay? Just warm up with one more. I don't think we need a lot of this. I'm not trying to reteach freshman calculus again, but I just want to make sure, in case you're wondering how to write some of these up, this would be good. So let's do one more. Let's make j of x be equal to the square root of x divided by x squared plus 4 sine of x. And again, I would like to find the derivative, j prime of x. So if that's my j of x, I just want to try to find the derivative of that. So the only thing that I think takes a moment's thought really is to try to identify, first of all, which of the derivative rules we're going to use. And then if they involve f and g, let's try to figure out what is f and what is g. Okay, that's the only thing I think we need to do here. And remember that the f is the inside function and the g is usually thought of as the outside function. And you can see that on the far outside, we have this big square root over everything, right? So what I would do here is let me start with g of x. I would let g of x just be equal to the square root of x. That is my outside function. Okay, so we're going to let g of x be the square root of x, and then f of x is the inside function. And for that, I'm going to use this entire quotient. So x divided by x squared plus 4 sine of x. So we could try to write it like that. I think that would be reasonable. And now we're just going to use the chain rule again. Let me come back over here. And hopefully I can I've got my heater going again, guys. Try to keep this board nice and warm. That's the secret to erasing it, that's for sure. Okay, so let's go ahead and use the chain rule. So by theorem 5.2, which is the chain rule theorem, right? So by theorem 5.2, h prime of x will equal, oh, you know what? Before we do that, let's come back over and write down the derivative of g of x here. So g of x is just the square root of x. The derivative of that, I think I did this one on Tuesday as well. The derivative of the square root function, you can think of it as an x to the 1/2. So by the power rule, it's going to be 1/2 radical x. So I'm going to use that derivative value on the right-hand side. Now this is going to be a little messier than the first example. So I'm going to take, according to the chain rule here, guys, I have to take g prime of f of c. So that would be 1/2 times the square root of, and now instead of x here, I'm going to put in what f of x was. So f of x was x over x squared plus 4 sine of x. So all of that, yeah, and then I have to multiply that by the derivative of f of x. And if we look at the f of x here, it's a quotient, right? It's a quotient, and I managed to preserve the derivative of a quotient here on the board. Let me see if I can squeeze it in right here. Low d high minus high d low divided by low squared. Let's put the low squared on the bottom. X squared plus 4 sine of x. That's all being squared in the denominator. And then, as I said, the numerator is low d high. So that would be, the low is the square root of x times the derivative of the numerator. Oh, I'm sorry. No. I did this wrong. Sorry. The low part is, we got to work with the f of x here. The low part, oh, I'll never fit this on here. Let me put a little star here, guys. I don't have enough room. I'll put what the star is right here. So it's just the quotient rule. Low, the numerator of the quotient rule, which is x squared plus 4 sine x times the derivative of x, which is 1, minus the numerator, which is x, times the derivative of the denominator, which is 2x plus 4 cosine of x, right? The derivative of sine is cosine. So all of that should actually go up in the place where I put that star in the formula. Does that look right? Check me out, guys. I want to make sure. Can you guys all see this okay? The board's clear enough? So what's going on over here is the quotient rule for the derivative of f, right? That's in the brackets on the right. The part in the front is just the g prime of f of c. So I just take 1/2 times the square root of whatever f of x was. Okay, so there's a couple good examples of derivatives, calculating derivatives using the rules. Are there any questions so far? Okay, so this is just a little bit of warm up for today. Let's go on. Erase this chain rule here off of my board a little bit. I didn't get my heater turned on quite fast enough, it looks like. That's coming on. Not too bad. Okay, I just wanted to mention, guys, a brief little moment to say something about higher derivatives. Obviously, once you take the first derivative of a function, you can then consult the idea of doing the second derivative or the third derivative or anything else, right? So it turns out that, so just make a quick little comment here about higher derivatives. Higher derivatives. So just a quick comment about that. The nth derivative, of f, which is usually just written this way, you basically write it as if n is an exponent, but you have to put a parentheses around the n. So n derivatives of f is the derivative of n minus 1 derivatives of f. So if we take the n minus first derivative of f and we take its derivative, then that becomes the nth derivative. And of course, this is only if it exists, right? That limit definition still has to exist. So let's just say provided that, I'll just say it this way, that the n minus first derivative of f is in fact differentiable. And this could be, at some point C, but I'll leave out the reference to the point C here. But you have to be able to take the derivative of the n minus first derivative in order to have the nth derivative, right? So that's about as much as we can say there. This shouldn't be anything too surprising, right? This is just saying that you can take more and more and more derivatives as long as the thing you have in front of you is differentiable. So nothing too surprising there. Okay, so are there any questions on that much? Tell you what, let's do an example involving the second derivative. I'm not going to just use the derivative rules though. I'm going to give you something a little more interesting to chew on. So let me clear this off and we'll do another example. I like examples, guys. Have you noticed that? Examples are awesome. So let's do another example. Come back over here and set it up. So I'll start off with an example here. Let's let f of x, I'm actually going to define it as a piecewise function. I'm going to let it equal x squared times the sine of 1 over x if x does not equal 0. And I'm going to define it to be 0 if x equals 0. So it's kind of a piecewise defined function. And I'm going to try to calculate the first derivative of this and then even the second derivative of it. So we're going to try to do two derivatives of this. We kind of have to do this in two parts because there's the c values that are not 0, right, for which we can really focus on the first part of the definition of this function. But then there's also what happens to the derivative at 0. Since it's a piecewise defined function, it's maybe a little bit unclear. So let's start off. So let's compute f prime of x and f double prime of x if possible. So I'm just going to say if possible. We're not quite sure yet if it's going to be possible, but let's just give it a shot. And you can't do the second derivative until you've at least done the first derivative. So you have to go in order here. And so for the first derivative, which is f prime of x, so now I'm going to start my solution. For the first derivative, I'm going to do sort of two cases. Let's let x be non-zero to start with. So in this first case, I'm going to let x be non-zero. And as long as x is not 0, right? As long as x is not 0, you realize I don't even need to think about the second part of the piecewise definition. For this, I can just use the formula on the top part. And for that, I'm going to use what? The product rule, the chain rule, and the quotient rule. Okay, so I can go ahead here and I can just say as long as x is not equal to 0, I am literally just going to use the product rule. So that'll be the derivative of the first term. So the derivative of x squared is 2x times the second term, which is the sine of 1 over x, plus the first term, which is x squared, times the derivative of the sine of 1 over x, which will be the cosine of 1 over x, times the derivative of 1 over x, which is actually negative 1 over x squared. So I'm just jumping to the answer right away here. I'm not actually trying to identify how I'm using the chain rule and the quotient rule and the product rule specifically. I'm going to clean this up just a little bit. The first term, I can't really do much with that. But on the second term, I can use a minus sign. And I can cancel the x squareds, it looks like. Right, so I can cancel those x squared, so it's just minus the cosine of 1 over x. That is going to be the derivative of f for every input other than 0. That look all right? By the way, thank you guys. If you've got your webcams on, I really appreciate it. If you don't have it on and you're able to, I would love to see more faces out there. But I'm doing the best I can to get some feedback through the computer here. That is for x not equal to 0. Let's try to calculate the derivative of f at 0. What about what if we let x equal 0? Because this is also this is a value where the function is defined. So let's go ahead and try to calculate. So sorry. What I need to do is I'm asking about f prime of 0. Right? I'm plugging in 0 now. Well, in order to calculate that, I am actually going to use the definition again. In this case, I need to use the definition, which is that we're going to take the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. So this is just going back to the very beginning of derivatives, where we take the limit definition, right? Take the limit definition. Okay, well, we know that f of 0 was given to us as 0. It was defined that way. So I'm really just, on the top and on the bottom, I'm literally just subtracting 0. So this just becomes f of x over x, right? And remember that when we're taking this limit as x approaches 0, x does not equal 0 while we're doing that. And so as long as x does not equal 0, the first formula up here at the top is what applies when x does not equal 0. So I can actually write this as the limit as x goes to 0 of, well, f of x is x squared times the sine of 1 over x, but after I divide that by x, I'll just get x times the sine of 1 over x. X times the sine of 1 over x. Okay, so that's the limit that we are looking at. And does anybody know what this limit is equal to? And I did say if possible, so maybe if it doesn't exist, it doesn't exist. But does that limit exist, do you think? Sine of 1 over x, right? That's bouncing between plus and minus 1. However, the x part is crushing it. The x part is going to 0. And so it's almost as if this is approaching something that is 0 times something between 0 and 1, between -1 and 1. Well, that's going to be 0, right? So this is actually equal to 0. This one does exist and it does equal 0. If you really want to make it precise, what you could do is you could say by the squeeze theorem. So we did talk about the squeeze theorem for functions back in chapter 4. And you could do that here. You could say, look, negative x is between, x times the sine of 1 over x is between plus and minus x. So I'm just going to show you here how the squeeze theorem would work. X obviously converges to 0 as x goes to 0. Negative x also goes to 0 as x goes to 0. And so by the squeeze theorem, the one in the middle, which is this dotted line, right, x sine of 1 over x, that would converge to 0 as well. Right, so that's how we can prove that that limit is equal to 0. Okay, hopefully that makes sense. I'm going to pause and see if there's any questions here. I kind of lost my chat window. Let me just make sure I got it back again. Okay, there it is. I don't see anything in the chat. I don't see any hands raised or any microphones going off. Is everybody good? Okay, good. I'm glad that it's at least making decent sense. So we've actually calculated the first derivative of f already. Let's write down what we've come up with. So what is the first derivative? F prime of x is equal to, and we can view this as sort of in two parts. It was when x is not equal to 0, we came up with 2x times the sine of 1 over x minus the cosine of 1 over x. And then when x equals 0, we came up with the derivative being equal to 0. We had to do that one directly from the definition. So this is now the first derivative of our function f of x. We started with f of x, we've calculated the first derivative, and now, once I'm confident that everybody out there is okay, we're going to work on the second derivative. The second derivative, I'm going to do it the same way. I'm going to look at the x's that are not 0, and then I'm going to look at what happens at 0. So I'm going to kind of do this in two parts. But let's go ahead and talk about the second derivative here. So this will be for f double prime of x, right? And let's see, again, what happens in these two cases. So the first case, if x is not 0, now remember, all I'm doing is I'm taking the derivative of the first derivative, okay? So again, I'm going to just use my rules of differentiation. In the case when x does not equal 0, I can do that. So let's see if we can get it right here. For the second derivative of f, I have two terms here. So I'll start with the 2x sine of 1 over x. So the derivative of that is 2 times the sine of 1 over x. And then plus 2x times the cosine of 1 over x times negative 1 over x squared. And then we have the derivative of cosine. I know I didn't do that one in class, but we proved that the derivative of sine is cosine. And by almost the same argument, we can prove that the derivative of cosine is negative sine. So in this case, we have a cosine. The derivative of that will be negative sine, and that turns that minus into a plus. And again, by using the chain rule, we have to multiply by negative 1 over x squared here as well. So this is only for the x's that are, this is, again, all of this is as long as x does not equal 0, okay? So as long as x does not equal 0, that would be the second derivative of f. Remember that the second derivative, you probably remember this from calculus, it measures the concavity of the graph of f. So concave up would be sort of bowl-shaped or U-shaped. That would be if the second derivative was positive. If the second derivative was negative, in that case, you're talking about a graph that's concave down. And so that means it's kind of shaped like the top of a hill, kind of sloping down away from you. So this would be the formula for the second derivative of f as long as x does not equal 0. But I also want to look at the other case, which is what if x does equal 0? So let's do that case as well. So the second derivative of f evaluated at 0. Again, I'm going to use the limit definition. I have to use the limit definition, actually. So I'm going to use it here. And so this time I'm taking the derivative of the first derivative. So this should be the limit as x approaches 0 of f prime of x minus f prime of 0 all over x minus 0. Okay, something like that. And let's see what we can do with this. If I just plug in what I know so far, this will be the limit as x approaches 0 of, the denominator is obviously x. In the numerator, we have to subtract the derivative of f at 0. F prime of 0 is just 0. So I actually don't have to subtract anything here. I just need to put in f prime of x, which comes from the top formula. That's 2x sine of 1 over x minus cosine of 1 over x. So that's in the numerator. And then we're dividing that by x, as you can see. And let me simplify that. Just do a quick little bit of algebra here. The first term is 2 times the sine of 1 over x. The second term is 1 over x times the cosine of 1 over x. Okay, so this is what you would have. And now the question is, does that limit exist? And if so, what does it equal? Right? That's going to be the question here. Does that limit exist and what does it equal? Well, actually, you might remember, we've looked at this before. Sine of 1 over x doesn't have a limit as x approaches 0. That's that wildly oscillating function that gets super, super tight oscillations as you approach x equals 0. So it bounces between plus and minus 1 in a very, very sharp fashion over a very, very small amount of the x-axis. So this doesn't exist to begin with. And if that's not enough to convince you, I can convince you even more that this limit doesn't exist if I just look at the second term. Cosine of 1 over x, that's also somewhere between -1 and 1. And then look what you're doing. You're dividing by x. Dividing by x when x becomes very, 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 very small means that this thing blows up. All right, so you have something that doesn't exist minus something that blows up to infinity, and that is a dne. So which is equal to dne. So there is no second derivative at 0. That just actually doesn't make sense. Does that seem okay to everybody?
Isn't that what we had for the first f prime of x? So that one doesn't exist either?
This one did exist. So if we look here, there's a slight difference, right? This limit is okay. X times sine of 1 over x, that limit does exist as x goes to 0. But if I didn't have that x there, if it was just sine of 1 over x, or 2 times sine of 1 over x, then it would not have existed. So we used the squeeze theorem over here to sort of show ourselves that x times sine of 1 over x actually does exist as x approaches 0. But without that x there, we can't use the squeeze theorem in the same manner, and the limit actually doesn't exist. Even a graph of it would convince you of that. Seem okay? Yeah, so it's really a subtle difference, right? I mean, I agree, looking at this thing here, 2 times sine of 1 over x compared with x times sine of 1 over x, they look very similar, but this one does have a limit that exists as x approaches 0. This one does not. So it's definitely worth reflecting on that a little bit, making sure you understand it. I mean, you can do a squeeze. So I could do this just to dispel anybody's second thoughts. You might think, well, why can't I use the squeeze theorem over here? Well, I can sandwich the sine of 1 over x between -1 and 1, but what's the difference? Over here, I had -x and x, which were going towards 0. -1 and 1 are not converging to the same value, right, at all. So that's a problem here. We can't really use that kind of a comparison or that kind of a squeeze application for this limit. Yeah. So some of this is going back to chapter 4, right? Of course, we're doing limits of functions here to try to evaluate derivatives. And this is why we had to wait till the second part of the semester to talk about derivatives, because a derivative is really a limit of a function. And so we had to have that whole chapter about limits of functions first. Yeah. Everybody good? Awesome. Okay, great. I want to spend the most of the rest of today talking about applications of derivatives. So let me give myself some space. We've done some good examples, but I want to do some applications if I can. And I'm going to erase over here so that I can do that. This is gonna be, again, some very familiar results, but we're gonna prove everything this time. Okay, so let's talk about some applications of derivatives. Let's get some applications of derivatives going. So I'll start with a definition that we're going to need in order to talk about this. This is definition 5.2. Another very good thing for your flashcards. So we'll set it up the same way. We're going to let f be a function from I to r, and we're going to let c be in the interval I somewhere. So c is an element of I. Then f has a local maximum. F has a local maximum at C if there exists a neighborhood, of C. I want to give this thing a name. Say the neighborhood is called U. There's a neighborhood of C, let's say U, such that f of x is less than or equal to f of c for all x that is in U and also in the interval I. So intersection of U and I. So, and then I'm going to say, let's just add while we're at it here, similarly for local minimum at C. Okay, so local maximums and local minimums. Guys, is very similar to the definition of an absolute maximum and minimum. But when we talked about absolute extrema, you may remember when we talked about absolute extrema, there was no mention of a neighborhood. It wasn't just, f of c was not just the largest value within a neighborhood. F of c actually had to be the largest value. It had to be greater than or equal to every other f of x value in the entire domain. So there is a subtle difference between absolute extrema and local extrema. In fact, this is worth maybe being our first little remark here, quick little observation. It's not really theorem worthy, but just as a remark, every absolute extremum is also a local extremum. Guys, when I use the word extremum, that's just my shorthand way of saying that I'm talking about both maximum and minimum in one word. So an absolute maximum will always be a local maximum, and an absolute minimum will always be a local minimum. Remember, we defined absolute extrema already. We did that even before we talked about derivatives, right? And I guess I could have defined local extrema back then as well. I could have told you what a local extremum is. You notice there's no mention of a derivative anywhere here on the board. So I don't really need derivatives to make this definition. But as we're going to see, derivatives are very closely linked with local extrema. You already know this from your freshman calculus courses, but we're going to reiterate those results and remind ourselves of those results and prove those results today. Okay? Is everybody with me? The converse of this remark, of course, is not true. You all probably got asked that question a million times. Give an example of a local extremum that's not an absolute extremum. So you can have, something like this. This is a local max, but not absolute. So that's a local maximum. So in other words, the converse is not true. You can have a local extrema, so that this is like a local high point. There is a neighborhood. There is a neighborhood here, I'll call it U. There's a neighborhood around this point C, such that f of C is the largest value. So it is true that for all x within that neighborhood, f of C is the largest value, but it's not the absolute maximum on the entire domain of this function. Because I've got other places over here that are higher. And so that's just something to keep in mind. One more little definition. This is not a huge deal, but we are going to need it in order to state our next proposition. So I'm gonna make one more definition. This is a minor one. This one is not so important, but I'm going to tell it to you anyway. C is an interior point of an interval I. So some of these results are going to talk about interior points of an interval. So you have an interior point of an interval if C is not an endpoint of I. So C should be just not an endpoint of the interval. As long as that's the case, we're going to call it an interior point of the interval. Okay, so sorry, I'm going to come around to the other side of my studio here, and we're going to state a proposition about local extrema. So again, just to reiterate, guys, we have defined local extrema without ever talking about derivatives. So this definition would work for any kind of function, even if it was not differentiable. But I know that you are aware there's a connection, and I'm going to try to spell that out for our notes here in this next proposition. There is a connection with derivatives to local extrema. And here's what it is. So suppose that f has a local extremum. Suppose that f has a local extremum at an interior point C in I. So let's suppose that f has a local maximum or a local minimum at some point C. Then if f is differentiable at C, can somebody tell me what would be the derivative of the function at a local extremum, assuming that that derivative exists? What's going to be the value? And I know you've seen this before. Yeah, Lila and John with their cameras, I can tell. You can throw your answers in the chat, guys. Those of you out there kind of on the dark internet side of it where I can't see you. Yeah, the derivative, of course, as you know, you can even see it here at this local maximum, the slope is 0. Remember, the derivative is really like intuitively the slope of the function, assuming that that exists. So the derivative should be 0, right? That's the proposition. So if we have a local extremum at some point C, then the derivative is 0. Now, before I prove that, I want to make a whole bunch of observations. I want to convince you that the converse is not true. I want to convince you that it's not true. So the converse is not true, and I'm going to convince you that all of these assumptions are necessary. So a couple of remarks before we actually prove this proposition, because that helps with the intuition. We have these remarks kind of spelled out first. So the first remark is that the converse of proposition 5.2 fails. And what does that mean again? That means that it's not the case that just because the derivative is equal to 0 at C, that does not mean that C is a local maximum or minimum. Do you have an example in mind? Can you think of a function and maybe a C value for that function where you have the derivative being 0, but without being at a local, without being at a local extrema? I'm sure they would have asked you this in your earlier calculus classes too. If you have an example in mind, why don't you type it into the chat? We'll just, and again, there's no pressure here. If you don't remember and you just want to take a stab at it, that'd be great. But I'm going to wait. I want somebody to think about a function where it could be flat somewhere. So the derivative being 0, but that flat spot is not a maximum or a minimum. Is there a function that comes to mind? Ooh, I need to get back to I need to get back to Fullerton so I can like pick on people a little bit more easily. Okay, I see in the chat some ideas, constant functions. You know, Hyanju, I appreciate that suggestion, and intuitively it totally makes sense. But because this says f of x less than or equal to f of c, it's a little hard to believe, but when you have a constant function, every single c value, the entire domain consists of absolute maximum, sorry, local maximums and minimums, right? So for a constant function, you're basically swimming in extrema, right? You're right that the derivative is 0, but I would claim that all of those points are actually local extrema. Amber's got a good one in the chat though, and this is the one that they usually show you. I know it's the one that I show my students when I teach Calc 1, which is, for my example, what I would do is use f of x equals x cubed. And as you guys know, the graph of that, if I want to draw the graph of x cubed, it kind of looks like this little sideways S shape. So that's the graph of x cubed, and you can see that right at 0. So let's just say at c equals 0. Right at 0, the derivative is 0. So here, f prime of 0 is 0. You can just see it from the graph, or you can just use the power rule and plug in 0. But 0 is not a local extremum. It's not a max, it's not a min. Any neighborhood you try to draw around that origin, any neighborhood that you draw here, guys, is going to contain some values that are larger than 0 and some values that are smaller than 0. You don't have an extremum there at all. So this is a great example that the converse of the proposition fails. Okay? It's also important that the function be differentiable at c. So my second remark here is that f must be differentiable at c. This kind of goes without saying, because if f was not differentiable at c, guys, you wouldn't be able to even talk about f prime of c. A good example of this one, we talked about this on Tuesday, a function that's not differentiable somewhere. And the nice example that is easy to write down is just the absolute value function, right? So that absolute value function, so here, c equals 0 is a local min. Here we have a local minimum at 0, but the derivative of the function at that value of c does not exist. And you can, of course, prove that directly from the limit definition, or you can just kind of look at the graph. Right? You've got a sharp corner right here at 0. That sharp corner tells you that this derivative is not going to exist. And we did that one on Tuesday as an example of something that's not differentiable. So you definitely need to have that. Right. Another feature of this, again, I'm still not quite doing the proof yet. Let me come back over to the other side. Another point here, guys, is that C does need to be an interior point. Notice that in the statement of the proposition, not only is f differentiable at C, but the C has to be an interior point. Let me give you another example. So maybe I'll call this another remark. Remark 3, C must be an interior point. C must be an interior point. Let's see if we can understand that. C must be an interior point. Well, I can give you an example. This one, I'm just going to give you an example with a picture. So I'm going to give you a picture here. Let's make our function have this interval I. And actually, let's include the endpoints. I'll make this a closed interval. And I'm just going to assume that this is C right here, right? So this is my C value on the left endpoint. So again, if I want to draw a graph, maybe I draw something like this. Here's f of x. Just that line like that. Well, using our definition, which I unfortunately just erased, but using our definition, in this picture, C is a local minimum. So we do have a local minimum at this endpoint. So here, C is a local minimum, but the derivative of f at C is definitely not 0. Even if you were to say that it actually exists. So maybe you have just a line. The function is just some line, mx plus b, but you constrained the interval I to be this closed interval. You might say, yeah, that derivative does exist right there. It's equal to whatever the slope of that line is, but that slope is not 0. So here's another remark. What I'm doing here, guys, is what everybody in Math 350 should be doing, which is that we take a statement and we think about its converse. We think about the hypotheses of the statement. We make sure that they all seem like they really are necessary. If something's not necessary for our results, we shouldn't include it in our assumptions. So I've tried to give you some examples here to show you that, yeah, we need all of these assumptions. And now, with all of that behind us, I'm ready to give you a proof here. And we're going to do this proof, and then we'll take a 10-minute break. Okay, one more result. This isn't too long of a proof. For the proof, I'm going to start off with this proposition. I'm going to assume f has a local minimum at C. Obviously, we also have to prove this for local maximums. Turns out that the book does the proof of the local maximum case. So that's why I'm focusing on the local minimum case to give you an alternative. So you can read the one in the book for the other case if you would like. If f has a local minimum at C, what does that definition mean again? I know I've erased it from the board, but we've got it in our notes from just a few minutes ago. This just means that there's a neighborhood around C such that f of C is the smallest value of any output of the function in that neighborhood. So in this case, thus, there exists, I'm going to call it delta greater than 0. There exists a delta greater than 0 such that For all X in the neighborhood that goes from C minus delta to C plus delta, by the way, if C was not an interior point of the interval, we might not be able to make a neighborhood that's within the interval. So the fact that C is like, C should be like right here, then I can make this neighborhood that's completely in the domain of the function. So we need this to be an interior point C. So for all X, which is in that neighborhood and X in I, we have f of X greater than or equal to f of C. So f of C is the local minimum. It's the smallest value of the function. And I would like to prove that f prime of C is 0. I'm assuming that the derivative exists, right? So then if we look at f prime of C, right? First of all, it's an element of R. I'm just gonna write this kind of off to the side. F prime of C is a real number. That's what this assumption here tells me. F is differentiable at C, so that does exist. But let's write it out as a limit definition. This is the limit as X approaches C of f of X minus f of C all over X minus C. All right. Well, that, as it turns out, I'm going to come to the other side again because I need a little more room. I'm going to try to prove that that has to equal 0. Let's get rid of these extra remarks now. If you don't mind, I'm going to just extend my big equal sign over so I can kind of come up here and use the board here. You guys probably remember that if a limit exists, which this one does, if a limit exists, then if I make any sequence that converges to C, right, that limit still has to, the limit of the corresponding sequence has to exist and equal the same value. So this is equal to, I'm going to do this in 2 pieces because I'm going to actually make 2 sequences. So you'll see how I'm going to do this in just a second. I'm going to take the limit, not as X approaches C, but as n goes to infinity. I'm going to make a sequence here. This is the trick. And I'm going to use f of C plus 1 over n minus f of C divided by 1 over n. Is that what I want? Yeah, so basically, I'm going to create a sequence. Let me just make sure I'm saying this right. Xn is like C plus 1 over n. For this case right here. So everywhere I see an X, I'm replacing it with C plus 1 over n. So you see in the numerator where I had f of X before, now I have C plus 1 over n. And when I do that in the denominator, of course, the C's cancel and I just get 1 over n. So we have that. If this limit exists, guys, then this limit should also exist. Because this is really just, these are just a bunch of values that are converging towards C. C plus 1 over n is converging to C, right? So I can plug that in for X on the top and on the bottom. But I don't have to use that sequence. I can use a different sequence instead, and I'm going to do that on the bottom here. And the sequence I'm going to use on the bottom, I'll write it down here on the bottom so you can see what I'm going to do. I'm going to use C minus 1 over n. And so this becomes f of C minus 1 over n minus f of C. Any sequence that's converging to C will work. And so I've got 2 of them here.
Dr. Annan, is that as n goes to 0 or infinity?
N goes to infinity.
Okay, I just
That's
wanted to be
sorry,
clear.
that's an infinity there. I'm so sorry. Yep, I can see that's hard to read. Thank you. So in both cases, n is going to infinity here. We're talking about the limit of the sequence. And so we get both of these expressions. Okay. But now here's the deal, guys. Here's the deal. Let's take a look at this first one. Would you guys agree that everything on this first fraction is positive? F of c, remember what we had over here? F of c is less than or equal to everything. So f of c plus 1 over n minus f of c, that should be positive, right? And 1 over n is positive. So I don't really know exactly what's going on with that fraction, but it's got to be greater than or equal to 0. It's got to be greater than or equal to 0 because in the numerator, we're subtracting something bigger from something smaller. What about the second formulation? On the second formulation, the numerator is the same thing. F of c is smaller than whatever's in front of it here. So the numerator is still positive, but now the denominator has a minus on it. So the numerator is positive, the denominator is negative, so guess what? That limit has to be less than or equal to 0. But of course, these are the same value. They're both equal to this f prime of c, right? So what we're saying is f prime of c is greater than or equal to 0, and f prime of c is less than or equal to 0. They're both true. And so that means that f prime of c is actually equal to 0. This is what we were hoping to prove. This is what we were hoping to prove. So in a little bit of an unexpected twist, we're using sequences again. Okay, does everybody remember how that works? If a limit exists as x approaches c, then we had a proposition back in chapter 4 that said, all right, if this limit exists, then if you make any sequence that converges towards c, and I actually made 2 of them here that both converge to c. If I make a sequence that converges to c, then this limit has to still agree with whatever that value of that limit is. So if f prime of c is what that equals, which it does, this is what f prime of c is, then both of these limits have to agree with f prime of c. But as you can see, the first one is a bunch of positive numbers, and the second one is a bunch of negative numbers. And the only thing they have in common is actually 0, which you can think of as being sort of right on the cusp of being positive and negative. Any questions on that? It's a nice proof, but it does rely on sequences. It takes us back just a little bit in the material. Okay, well, I didn't tell you this before, but we're going to do some of the most famous theorems in calculus today. Not the fundamental theorem. That's going to come on the very last lecture of the semester. The fundamental theorem of calculus is going to be my triumphant climax in about 3 or 4 more weeks. But we are going to do Rolle's theorem and the mean value theorem and some other results relating derivatives with slopes today. So we're really in application mode now. If we weren't already, we definitely are now. But that's just my way of enticing you to come back in 10 minutes. I'm going to give you a break from screen time until 2:20. So in about 10 minutes, we'll turn things back on, and I'm going to prove Rolle's theorem and the mean value theorem for you. I'll see you shortly.
Professor, the bottom part of that piecewise you wrote over there with the limits, why wouldn't the numerator be a negative? Because you're subtracting a bigger number from a smaller number.
No. F of C is less than or equal to everything. That's the point. We're assuming that F of C is a local minimum. So that means that even though it's true that C minus 1 over n is less than C, but F of C minus 1 over n is greater than or equal to F of C.
Gotcha.
That's it.
Okay.
Yeah.
Thank you.
Good point. Thank you for bringing that up. You're making me hungry out there, John. Guys, if you're out there within the sound of my voice, I'm gonna start again in about 1 more minute. So this is a good time to find your way back over to your computer and if possible, turn those cameras on so I can see your pretty faces out there. We'll get started shortly. Are you in the basement, Amber? Yeah? Okay. Has it been quiet there this week since I'm not there, or is it just like normal?
It's been a little quieter, but I think that's just the post spring break.
Is everybody sort of having a coma after spring break like usual? Because that's usually what
Yes.
happens. Yeah, that's
Yeah,
that's
but
always what
to-
happens. Everybody's doing great, and then they make us go away for a week, and we come back, and it's like everybody's like starting.
Yeah,
Gotta get their rhythm back again, and that
Mhm.
first week back can be tough. So.
exactly. But Jose's here today, so it's loud again.
Oh. Okay. All right, well, guys, I hope that you're all out there again. I see a few faces at least, so that's a good thing, and thank you for that. I think I'll go ahead and pick things back up. We only have a half hour left, but this half hour is going to be pretty action-packed because I have a lot of pretty big results from calculus to share with you, and I hope that almost everything, there shouldn't be anything I'm going to say the rest of today that's surprising. Like these are results that you're going to know and you're going to hopefully be familiar with. And even if they're not on the tip of your tongue, as soon as I sort of draw a picture or write it down or whatever, I hope it'll be something that comes back to you that, oh yeah, of course that makes sense, right? That's my fingers crossed, my hope for this, but let's just see how this goes. I was a little surprised that our book does not state Rolle's theorem as an actual theorem in the main body of the text. Instead, they've got it buried in the exercises from section 5.1. So if you're looking through your book trying to figure out where's Rolle's theorem in the book, well, it's actually one of the exercises from 5.1, but I think it's too important to just leave as an exercise because we're going to want to use Rolle's theorem. For one thing, we're going to use it to prove the mean value theorem that is even more famous and which is going to come very shortly as well. So I think we need to do this one in class as a main part of the lecture because it is just too important just to sweep it into the exercises. So let me state it for you here. Rolle's theorem, I'm sure you've seen this before, but let's just get it back up in front of us. So if f is continuous on a closed interval AB. Now, a week ago, we had a lot of theorems about continuous functions on closed intervals, but they didn't involve derivatives. A week ago, the results were not about derivatives. Things like the intermediate value theorem, the extreme value theorem, there were no derivatives in that. So today, we're going to come back to this same sort of standing assumption that f is continuous on a closed interval, but there's a differentiation component to this, which is that f is continuous on the closed interval, but it is also differentiable on the open interval AB. So it needs to be differentiable throughout the interior of the interval. And one more assumption, f of A equals f of B equals 0. So if the function is equal to 0 at the endpoints of the interval, then there exists a C in that open interval AB such that f prime of C is equal to 0. Okay, so that is the statement of the result. And I kept our proposition from before the break on the other board over here because we're going to use this previous proposition to prove Rolle's theorem in a moment. Just to get you back in the groove of this result, you know, if you have a closed interval AB, and if f of A and f of B are both equal to 0, and then your function is continuous and differentiable, which basically means it's got to be smooth. you know, your function might look something like this. Well, then there has to exist a point C somewhere in that interval where the derivative of the function is equal to 0. So the intuition behind this Rolle's theorem is kind of what this picture is trying to show you here. Okay, let's write down the proof of this theorem, and then the application will come very quickly once we write down the mean value theorem. One possibility, and it's kind of like a special case that I'm going to dispense with first, is it's possible that f of x could be equal to 0 for all x in the closed interval AB. If that happens, if my function is just the constant function f of x equals 0, then any c in the open interval AB will work. I think you would agree, right? That if my function, okay, I'll draw a picture, but it's kind of a silly picture. If my function is literally just the y-axis, right? If this is my function here, just f of x always equals 0, then you can pick c to be anything. Any of these points would be fine. And the derivative, as you can see, the slope of this function would be 0 at any of those points. So that's kind of the picture. That's kind of the picture that would go with that first case. So now what I'm going to do is I'm going to consider the possibility that maybe f of x is not just always equal to 0. So otherwise, there exists some x in the open interval AB with f of x not equal to 0. So in this case, there would be some f of x not equal to 0. I'm just going to assume, without loss of generality, I'm going to assume that f of x is actually positive, which is how the example I've got here on the board, the way the picture is I've drawn, that would be the case. It would be possible that f of x is always negative, and that would just be another case. So I'm just going to do the case when the function is always positive, without loss of generality. Okay, well guys, what I'm going to do is I'm going to apply the extreme value theorem. Do you remember this from chapter 4? The extreme value theorem says that if f is continuous on a closed interval, then it has an absolute minimum on that interval. And so I'm going to write that down. So by the extreme value theorem, I think that was theorem 4.2. If I remember correctly. Again, I don't have my book with me for this little hiatus, so I'm hoping that's correct. I think that's right. Then f attains an absolute minimum at some value. So it attains an absolute minimum in the closed interval AB, and sorry, not in, on the closed interval AB. Let's just say at C. Okay, so that would be at C, and obviously, so clearly. Did I say minimum? I said minimum. I meant maximum. I mean, it is true that it obtains an absolute minimum, but I need to, for this proof, I need to do maximum here. Sorry, I couldn't read my own writing. This should say absolute maximum. Can you guys fix that for me? So there's an absolute maximum. I mean, you can see it in my picture. The C value is going to give me an absolute maximum here. So that should say that f attains an absolute maximum at C, and the value of f of C, if it's going to be an absolute maximum, it has to be greater than 0. Because we've already got at least one f of x value that's greater than 0. So your absolute maximum has to be greater than 0. And because f of C is greater than 0, then that tells you that C is not equal to A and it's not equal to B. Because f of A and f of B are both equal to 0. So if f of c is greater than 0, then that means that c actually lives in the open interval AB. So c is actually in the open interval AB here, because it doesn't equal A and it doesn't equal B. Okay. So what do we have? We have this point C, which is an absolute maximum. That actually means, as well, I should also point out that this means that C is an interior point of my interval, I'll call it I, which would be just the interval AB, closed interval AB. So it is an interior point of that interval. And C is also a local maximum of F. Remember that? Anything that's an absolute maximum is also a local maximum. So if I have a local, so look how I'm setting myself up over here. I've got my proposition. What does this proposition say? It says, suppose F has a local maximum at some interior point of your interval. If the function's differentiable there, which it will be because we're assuming that F is differentiable everywhere in the interior of the interval, then if that's the case, then we're ready to just write down the conclusion. That this means that therefore, by proposition 5.2, we conclude that f prime of c is equal to 0. Right. So there has to exist a point somewhere in that interval where the function has a derivative equal to 0. This is what this is saying. Okay? And we can use our previous proposition to immediately conclude that after we've set everything up as we did in the first part of the proof. Does this make sense? Nothing too bad about that. That is just the case when f of x has a value that's greater than 0. But again, if f of x had a value that was less than 0, then we could still run this same proof, but we would be working with minimums instead of maximums in that case. Okay, well, with that result, if everybody's okay with it, we are going to jump to another very famous theorem. And I'll state it over here and then we'll prove it over on the other board. This is in the book, it's theorem 5.5. And this is the famous mean value theorem. This is the famous mean value theorem. So let me go ahead and state it here. You can abbreviate that if you want in your work as MVT. I'll know what that means. So the mean value theorem, the MVT, and it just says that if f is continuous on the closed interval AB and differentiable on the open interval AB, then there exists a C in the open interval AB such that f prime of C is equal to f of B minus f of A all over B minus A. That's the mean value theorem, the statement of it. All right, I'm going to erase over here for a moment. So that, I hope, maybe looks a little bit familiar as well. This is a famous result. We can draw a picture for this also, which I think I'll do. So let's draw a little picture of this. Here I've got my closed interval from A to B. And let me just draw a function, looks something like that maybe. So there's my f of x. I got a graph of f of x here. And what you'll notice is that f of b minus f of a divided by b minus a is actually kind of the rise over the run, the slope, in other words, connecting these 2 points. So this is the point a f of a, and on the other side we have the point b f of b. And so if you look at the change in y divided by the change in x, that's what that fraction is representing. And so it gives you this slope. So let me just draw, I'm going to draw a dotted line here. Right, so the slope of that dotted line is f of b minus f of a all over b minus a. Yep, and what the theorem is telling us, guys, is that there is some point C, I'm going to estimate it to be right there, where the slope of the curve right at C, so the tangent line, you guys have talked about this in calculus, I'm sure the slope of that tangent line is exactly the same as the slope of this, what's called a secant line connecting the points at the ends of the interval. Does that look familiar? So the 2 lines here are supposed to be absolutely parallel because they have the same slope. So the f prime of c is just the slope of the tangent line to the curve f of x. And the dotted line down here is just the slope of the secant line that connects the 2 endpoints of the interval. And there has to exist this point C. I do want to mention that in both Rolle's theorem and the mean value theorem, they don't tell us how to find C. So we don't have any, information about how to come up with the C. All we know is that it exists. But for pure mathematicians like me, half the time that's all I care about. If we can't figure out what C is and actually apply anything, I'm usually okay with that. Now there's something kind of interesting here. You might notice that if we take the mean value theorem and we plug in f of a and f of b both being equal to 0 in the formula for f prime of c, you actually recover Rolle's theorem. So I just make it as a remark here. My remark is that Rolle's theorem is a special case of the mean value theorem. It's actually a special case of it. In other words, if I had just proven the mean value theorem first, you're probably wondering, well, Dr. Hannon, why didn't you just do the mean value theorem first so that you could then just deduce Rolle's theorem as an immediate corollary? Well, there's a good answer for that, which is that I'm actually going to use the weaker theorem, which is Rolle's theorem, to prove the stronger theorem. This is going to feel a little weird, but we're going to use Rolle's theorem to prove the mean value theorem. Once we know the mean value theorem, we could, of course, go back and rederive Rolle's theorem much easier as a special case of the mean value theorem. Does everybody see that this Rolle's theorem is really just a simple version of the mean value theorem? If you just put in 0 for f of b and f of a over there, well, then you get f prime of c equals 0, which is exactly what the conclusion of Rolle's theorem is. So if we had started with the mean value theorem, we could have deduced Rolle's theorem in half of a heartbeat as a special case. So, but that's not the way we did things. That's not the way we did things. We proved Rolle's theorem first, and now I want to prove the stronger theorem, which is the mean value theorem. So let's get into the proof here. The proof of the mean value theorem. I should point out, this proof is not that hard. and it's an extremely important theorem in calculus. So this is one you probably ought to know. Not just the statement, I would make sure you know this proof as well. There's just one little trick, and it's right at the beginning, which is that we're going to have to apply Rolle's theorem to the correct function. We're not going to apply Rolle's theorem to the same little f that's in the mean value theorem. We're going to make a new function. And here's how we're going to do this. And this is kind of being pulled out of the sky. So I don't expect that you would come up with this on your own. But once you see me write it down, we will be able to use it and verify that it really does work. So I'm going to call it capital F of x. And this is going to be defined as follows. Little f of x minus little f of a minus the fraction f of b minus f of a all over b minus a times the quantity x minus a. Can everybody read that okay? Okay, I hope that's easily readable. You got to get this right. Okay, make sure you don't have any typos when you're copying that down. But if you look at capital F of x that I've just created, it's defined in terms of little f of x along with some values like f of a, f of b, a and b, which are all just numbers. So this is a function that I should point out, note that capital F is continuous / differentiable in the same places that little f is. It's continuous and differentiable in the same places that the little f of x is. We're not dividing by 0 anywhere. We're not doing anything too weird that way. So this is a function that is still very nicely behaved. It still behaves really, really nicely. Okay, well, what I'm going to do, guys, is I'm going to apply Rolle's theorem, not to the little f that we have in the statement of the mean value theorem, but rather to the capital F. Because by the way, did you guys plug in capital F of A yet and capital F of B? Let's look at it. What is capital F of A? If I put in A everywhere I see X, I hope you can convince yourself that that is equal to 0. Capital F of A is 0. And if you also plug in if you plug in B into capital F, you will also get 0. So that's pretty easy to see it. If you just put in everywhere you see an X, put in either A or B, you're going to get 0 as an output. And I am now set up to use Rolle's theorem. I have capital F being continuous and differentiable everywhere that little f was. I have capital F of A and capital F of B equal to 0. So then by Rolle's theorem, which we've already proven, by Rolle's theorem, there exists a C in that open interval AB with capital F prime of C equal to 0. So the derivative of capital F is 0 when I plug in C. Now, the thing is, if we take a look at what capital F is, we can just calculate its derivative. What is capital F prime of x? So guys, this is the thing that's driving the whole proof. This creation of this capital F function. What is its derivative? Well, I see that it's equal to little f prime of x. The derivative of a constant is just 0, so the f of a goes away. What about the second part? Oh, there's an x here that has a multiple in front of it, which is this f of b minus f of a over b minus a. So something like that, right? And that should be the whole thing. That is capital F prime of x. It's little f prime of x minus that part in the brackets. That's the derivative of it, just using your basic derivative rules. And so what does this formula give us for f prime of c, capital F prime of c? Well, it's gonna be little f prime of c minus f of b minus f of a all over b minus a, which is just a constant number, by the way. And so let's put these together. F prime of c is equal to 0, but it's also equal to this expression we just came up with. And if you put those two boxes together, guys, if you just put those two boxes together, you're gonna get the conclusion down here, right? This is what we're trying to prove. The mean value theorem down here on the bottom of my board, right? So thus we can immediately write that down. Thus little f prime of c minus the quantity little f of b minus little f of a all over b minus a, all of that is equal to 0. Make sure you're writing your big F's and your little f's in a way that you can clearly read. But that's a check. That finishes the proof of the mean value theorem. Okay. So far so good? Any questions about that proof? It's mostly just using Rolle's theorem. The trickiest part is coming up with the capital F of x here. And again, that's not something that you would just do in a snap of the fingers. This would take some time to figure out, how do I engineer this function? It needs to be engineered so that when I plug in a or b, I get 0, and such that its slope is exactly what I need in order to get my conclusion of the mean value theorem. But it's a nice proof. There's not, other than coming up with the capital F function, the rest of it kind of just runs itself. There's not a whole lot that you have to figure out from scratch on that. Okay. I'm gonna erase Rolle's theorem here, if that's all right. Obviously, the mean value theorem gets used heavily in calculus. It's one of the most famous results, but there's actually an even stronger version of the mean value theorem. We can go even a little bit more strong than this, and I'm going to state this theorem. I don't think I'm going to prove it today, but I want to state this is theorem 5.4, and it is called the generalized mean value theorem. So it's even a little bit stronger than the one we just wrote down. But it's also a little messier. It's not quite as nice as the one that we just looked at. I should mention, you might notice that my numbering is, well, I'm following the book's numbering, but you might notice that we just did theorem 5.5. And I've now numbered this one as 5.4. And there's a reason for that, which is that you can actually do theorem 5.4 first if you want to, and then deduce the regular mean value theorem as a corollary. So if anybody doesn't like the proof that I just gave you for the mean value theorem, there's another way to do it, which is to take this result, which I'm going to write down in a moment, and use a special case of it to prove theorem 5.5. And that's essentially how the book is able to do it as well. Let's state this theorem here really quickly. It just says the following: if we let little f and little g, so this time there's two functions involved, that's part of why it's a generalization. I'm going to let little f and little g be continuous on the closed interval AB and differentiable on the open interval AB. So just like before, right? So this is just the way the regular mean value theorem works, except now I have two functions here, which are f and g. And then there exists a c in the open interval AB. So this is reading just like the mean value theorem we looked at a moment ago. There exists a c in the open interval AB such that, and now I'm going to give myself a little more room. Actually, I can just clear this all off. I don't need this proof really for what I'm doing now. So this should look very, very similar to the regular mean value theorem, except here I have two functions, f and g, and now the conclusion is a little more murky than the one that we had over here. So this is what I don't like about it. It's just not quite as clean. Little f of b minus little f of a, right? Put that in brackets, times g prime of c is equal to, and then on the other side of the equation, we just reverse the roles of f and g. So g of b minus g of a times f prime of c. So that's it. And so this is a more generalized version of the mean value theorem. Now, if you, so just as a remark, and then we're just about out of time, this will be it for today. But if we, taking g of x just equal to x in theorem 5.4, if we do that, let's just, without writing anything down, I just want to look at it. If we just take g of x equal to x, then this becomes b minus a. And the derivative of x is just 1, so this just goes away. You see what you have? F prime of c is equal to f of b minus f of a over b minus a. So it just gives you the same formula over here again. So we recover the regular mean value theorem, which is 5.5. So this is another way to prove the regular mean value theorem, is to first prove this one, prove the generalized mean value theorem, and then from there, you can just plug in g of x equals to x and just let all of the things get plugged in, and you recover the formula for f prime of c down here. So that's a second way of proving the mean value theorem, but it does force you to prove this theorem first. This one I'm probably going to do in the group work. We probably won't do it in the lecture. It's not that interesting. You have to create a capital F of x again. That's kind of clever, just the way we did with the regular mean value theorem. But this one's a little trickier. So we might set up some hints and put it into a group work or something for next week. But I think I'm going to leave it at that for now, since I'm kind of out of time. We have another week or so to go on derivatives, and then we're going to switch over to integrals. It's kind of where we're at. Guys, thanks for your time today. I really appreciate you being here. And I also appreciate you coming to Zoom instead of going to the class for this week. It's been really helpful for me to be here for my folks. But I am coming back this weekend. I think I've got them in pretty good shape now, and I should be good for the rest of the semester. So thank you for being here. I'll hang around for another minute or two if there's any questions, but otherwise you're certainly welcome to go. And we'll touch base over the weekend. I'll send you another email. So thanks so much, guys. Bye for now.